The first talk of the day is going to be by the Canary. So here is the, I don't know what is the role of the chair. I mean, you can read the title. Well, happy that you're here.
Oh, you put them up. Let me turn this on. Ah, there we go. Okay. You know, I know some of you were probably disappointed because you looked at the didn't look at the schedule change, and you expected me to be Amy Wilkinson. And I understand because I'm also disappointed that I'm not Amy Wilkinson. So I wanted to start the talk with a quote from the immortal bard of my generation, Patti Smith, and I think she maybe was thinking about Dennis when she wrote this. She says, "From the geometry of his heart, he mapped it out. He saw the king rise, fitted with armor, set upon a white horse, immaculate cross in his right hand. He advanced toward the enemy, and the symmetry, the perfection of his mathematics caused the scattering of the enemy. Agitated, broken, they fled." So, what song is that? Constantine's Dream is the name of the song. Anyway,
Actually, I joined them.
You what?
I joined them.
And anyway, so I've known Dennis for a very long time, almost 40 years now. And I first met him when my cohort of Thurston students used to trudge up here from the fetid swamps of New Jersey to the fetid streets of New York. And we would go to Dennis's course, and then sometimes Bill would come along in the afternoon, and we would get to listen to the conversation. Listen to the conversation of mathematical giants. Not that I understood a lot of it, being more of a mathematical dwarf myself, but the best part of it really is that Dennis would take us out to lunch, and then he would just talk with us, a bunch of knuckleheads. And I think I told the same story last time I spoke at a Solvent thing, but it meant a lot to me at the time. It was kind of inspirational to me. He said, "You know you're really onto something when you have 100 wrong proofs a day," which is very true. Of course, sometimes you're just, full of it, but it's true when you're about to prove something, you have 100 wrong proofs per day. Okay?
Sorry.
No.
Which one is it?
That one.
Yeah, okay.
Share.
Is that up?
Press the green button on the top left.
Yes, sir.
You told me not to touch that. Now you went and touched that?
Green, there's a green circle.
Green button.
He's go right.
No.
That corner of it, there's three. Next to the.
Yeah, plus click. Oh.
There we go.
Sorry.
Okay, so I'm going to try to give kind of a gentle, not too technical introduction to the Hitchin component. So actually my abstract was a little more technical, and I decided for this, rather heterogeneous audience would be rather to do something just a little bit breezier. So the motivation for a lot of what happens in the Hitchin component, and in general what's known as Higher Teichmuller theory, is that it takes inspiration from classical Teichmuller theory. I just kind of remind you of a few basic facts about it, which will come up later. So recall that PSL2R, we think of that as the group of isometries of the hyperbolic plane, and then you have a discrete torsion-free group. The quotient of that is a hyperbolic, quotient of that is a hyperbolic surface, okay? And then we want to think of an identification of that hyperbolic surface, the fundamental group of that hyperbolic surface, the fundamental group of a base surface S. We think of what's called a Fuchsian representation. It's a discrete faithful representation from the fundamental group of a closed surface into PSL2R. and its image group, that is a Fuchsian group, and we look at the quotient, and it's a surface which is got the homotopy type of the closed surface S, so that the homeomorphism type of the closed surface S. And then we want to look at the space of all Fuchsian representations of a given surface group up to conjugacy. And we call that Teichmuller space. You can think of this, and this sits naturally, it's a component of the representation variety modded out by conjugation, and it has this nice property that's diffeomorphic to a ball. In fact, analytically diffeomorphic to a ball. And we can think of this as the space of marked hyperbolic surfaces homeomorphic to S. And then it naturally arises, of course, and you can think of it as the orbifold universal cover of moduli space, which is the space of sort of unmarked hyperbolic surfaces. And think of the marking as the representation marks the fundamental proof, or you can think of the marking, you can think of a hyperbolic surface as hyperbolic clothing, and the marking as instructions for how to wear that clothing. Okay, so please heckle me, because I would really hate to sit here with 50 or 60 of you in dead silence. It would make me feel bad. You don't want me to cry up here. So.
I think there's something wrong with the definitions.
What?
Now you will cry.
Now I'm going to cry.
More than one conjugacy when the one surface has symmetry. Conjugacy is not unique.
Oh, I mean conjugacy of the representation, not conjugacy of, the surface. Yeah. I mean, you take the space of homomorphisms, you identify two representations which are conjugate.
Oh.
Yeah, that's it. Yeah. Okay, and then you say, well, okay. For years, my office was right between the office of Ralph Spatzier and Gopal Prasad. And, they would just look at me and say, Dick, you've been doing this for 25 years and it's only two Lie groups, PSL2R and PSL2C. I decided to enter the world of higher Teichmuller theory. So you want to look at representations of a surface group not into PSL2R, but PSLDR. And if you're like me, you think you stick PSL2R into PSLDR, you stick it up in the upper right-hand corner and move on. But that apparently is not the smart way to do it. The smart way to do it is to look at the irreducible representation of PSL2R into PSLDR. That's unique up to conjugacy. And then you could get an irreducible representation of a surface group into PSLDR just by composing a Fuchsian representation with the irreducible representation. That's called a D-Fuchsian representation.
Is there a typo there in the first one? Yeah.
Oh, yes. Yeah, the first D in the second line should be a 2. Sorry. Yeah, sorry about that. So now, what Hitchin said is let's just look at all representations that you start with the D-Fuchsian representation and you just wiggle it. And look at anything which is obtained by deforming a D-Fuchsian representation is called Hitchin. And by definition, that's a component of the representation variety up to conjugacy. Okay, this is called the Hitchin component. And Hitchin, using rather analytic techniques.
It doesn't factor through the PSL2R. It's met from the fundamental group to
Right.
PSLDR, but it doesn't factor through.
Right, if it factors through PSL2R, it's called a Fuchsian, and then you just take that one and you wiggle it. And you wiggle it however you want. And he proved that it's real analytically diffeomorphic to RD squared minus 1, 2G minus 2. So when D equals 2, that agrees with Teichmuller space. And then he asked, well, what is the geometric significance of these Hitchin representations? And if you come from PSL2R, you might hope they're all going to be nice. But if you come from Klein groups, you say, well, if I take a Fuchsian representation, stick it into PSL2C, and just wiggle it, it's eventually going to become garbage.
What?
Well, it's eventually going to, if you just wiggle it enough, it's eventually going to become indiscrete, have indiscrete image.
For a little while.
Locally, for a little while it'll be fine. but he's looking at the entire
Oh,
component.
the entire.
So he called this the Teichmuller component in analogy. He did not call it the Hitchin component. He called it the Teichmuller component in analogy. With Teichmuller theory, he asked, well, what does that have? What do these representations have to do? His techniques didn't tell him anything about those representations. Well, some things, but so what? So there were two kind of viewpoints to attacking this. One of them is more algebraic, due to Fock and Goncharov. I'm going to tell you about Labourie's viewpoint for studying these representations, which took a more dynamical viewpoint. And if you want to be confusing, you could say, you look at the flow parallel to the flat connection on the flat bundle. Oh, I'm sorry, I'm keep walking. The flow parallel to the flat connection on the flat bundle. And if you're like me and you don't really know what a connection is, this is confusing, but let me just tell you it's something really very simple. So first of all, what you do is you look at the unit tangent bundle of H2 and cross it with RD, and if you have one of these Hitchin representations, the group acts on that bundle. It acts on the first factor, just the way the Fuchsian groups acts on H2, and it also acts on the second factor by rho of gamma. So then you quotient it out, and you get what's called the flat bundle associated with representation. It's just a vector bundle over the unit tangent bundle over the surface. So Y dynamics, where there's a
So
flow.
you made it discrete, you could form a quotient. You couldn't form a quotient before, right? You said it's not, when you deform it, it's not discrete.
Right, well,
You get garbage.
this flat bundle makes sense for any representation, even if it isn't
Sure,
discrete.
no,
Yeah.
that's what I'm saying.
Yeah.
This point, this construction allows you to not have garbage.
Right,
Okay, that's when your previous remark.
right. Well, in fact, it's going to turn out that Hitchin representations are not garbage.
Right.
But,
No, but you have to do
Yeah,
something, start
yeah.
this.
yeah, we have to prove that, right, yeah.
Yeah, yeah,
Right. So,
So can you explain better? So what is this? So you have the fundamental group.
we think of the fundamental group as a Fuchsian group,
Yeah.
and it acts on the unit tangent bundle, just as a Fuchsian group does, acts
Yeah.
by the derivative. And then, so if you take, so a point in T with H2 cross RD, you can think of as a pair of vectors.
Yeah.
One in the unit tangent bundle of H2 and one in RD. And it's acting on, in the first factor, just by the derivative of gamma. And on the second factor, by rho of gamma, which is an element of PSLDR. Or you really should think of SLDR, should lift this to SL. I'm going to always ignore the difference between PSL and SL.
How do we remember the form from an irreducible one? This makes sense for any representation.
This makes sense for any
So
representation.
how do we remember the hypothesis in terms of this construction?
Well, I'm going to tell you a theorem
Okay.
that uses
That would
that
be the
hypothesis.
okay.
I'm not going to prove the theorem, but I'll tell you. I'm going to tell you what we're going to conclude from that. And there's a flow sitting around here, which is called the flow parallel to flat connection. And it might just better be called the stupid flow. It's kind of the obvious flow. You look at it, the universal cover. The universal cover is just the geodesic flow on the unit tangent bundle and does nothing on the second factor at all. And then that descends to a flow on the quotient, and that flow on the quotient is now an interesting flow.
So the geodesic flow gives a flow.
Geodesic flow gives a flow, right? So you get a flow on the flat bundle which sort of lifts the flow on the base. This is a bundle, vector bundle over the unit tangent bundle, right? And you have a geodesic flow on the unit tangent bundle that lifts to a flow on the vector bundle over, flat bundle over it.
Just via the connection,
Yeah, or just,
just by the formula.
just by the obvious thing. Yeah, I'd probably, if you understand connections, that might help you. But yeah, so what Laborie shows, the main theorem of his paper is he shows this flow has a splitting into line bundles.
Well,
And
you mean in the case of it?
if rho is a Hitchin representation,
Hitchin, okay.
it has a splitting into line bundles. And moreover, if you take the ith line bundle and you direct sum it with it, that should be tensor product there, I think, LJ star, then that is a line bundle which is uniformly contraction.
You have to say tensor.
That should say tensor, yeah, that's fine. My mistake. Okay,
That's cool.
so this is a very strong result.
What is LJ star? Because you have the, when you put Li, LJ star.
It's the dual.
It's the dual.
Okay.
Is the dual, yeah.
This is uniformly contract.
Yeah, I'm going to show you what that means in practical terms on the next slide.
And
So,
this is easy to understand when you have a small deformation
right.
from these two is kind of obvious.
Right. So this is he started from a very dynamical viewpoint. For the Fuchsian case, it's obvious this splitting exists. It just lifts from the Fuchsian picture, and then it's obvious.
Why is it obvious?
Well, you just look at the Veronese embedding, basically.
Oh, okay.
Yeah, and then my basic dynamics, by these contraction properties, says that's locally stable, and what he has to show is, so this is obviously an open condition, and then he has to show it's a closed condition, and therefore it's true on the entire component. That's how the proof goes. It's a 50-page paper, but it's kind of the proof that kind of it must be, right? He studies what limiting properties arise. So if you look at, so let's think about what this tells us. If you take a vector, which is, that should be in T1H2. That vector is in T1H2. It's tangent to the axis of gamma and points towards gamma plus. Then if you look at gamma in that vector, it's phi t gamma of v. So you just take the translation distance of gamma, and you flow time t gamma, and there you go. But now, since each LK tilde is flow invariant, it follows that LK tilde restricted to v, which is a line in RD, is an eigenline. So what this particularly contains is this is a decomposition, so that sitting over the axes of hyperbolic isometries in gamma is just a decomposition into eigenlines. Now, what does that contracting property tell us?
What's E rho tilde?
It's just the lift. That was T1H2 cross RD.
What? No. Why do we have two things? I only have one picture in my head. It's got the bundle and splitting into line bundles, right?
Right, and now we're going to lift that up to the cover. So we have
To where?
We have a vector bundle over the unitangent bundle of the surface, and now we're going to lift it up to a vector bundle over the unitangent bundle of H2.
Oh, okay.
That's all it is. That's all this L tilde. That's all. Whenever we're doing tilde, it's often much easier to understand this practically to work at the level of the cover.
Right.
And so we see that these are eigenlines, and that if we let lambda k be the modulus, now what does it mean that Li tensor Lj star is contracted? Well, if for any k you let Wk be, so first of all, being contracting means you're contracting with respect to some norm, which is group invariant on your bundle, right? And because the base is compact, contracting with respect to one norm is contracting with respect to any norm. Okay? And so what you take a unit bundle, you take these unit tangent vectors, and we use the fact that Lk tensor Lk plus 1 star is contracted. And what does that mean? That means that if we flow time t gamma of Wk, and then we find flow phi t gamma of Wk plus 1, then the ratio of their norms is going to be is going to be less than some constant a, e, negative b, t gamma, which is the ratio of the norms of the original.
In that case, should be D in that line there, the inequalities.
No, that's k. Steady k.
No, the line of inequality.
Oh, that last one, yes. Sorry, you're right. Yeah, you're right.
So you have a period.
That should be d. Yeah, you're right. So if you see with phi t gamma Wk is just Wk over lambda k, and then you can pull out phi t gamma Wk is Wk sitting over the point which is flowed by t gamma. But that's gamma the point, so use the invariance of the norm says that you're divided by lambda k. And so you get, this tells you that lambda k is bigger than lambda k plus 1.
This is dominator speaking though.
Yeah, that's the other way to think about it, yes. And that's Andre's Andre's and Boki's viewpoint on it.
Dominated splitting was introduced by Manin. The notion of dominated splitting.
Yeah, so Lavary doesn't use that notion, but it's, you know, Andres and Jean Boki really take advantage of that in their work. And poetry is also that.
But what's the that in a sentence?
The fact, you could think of this as being related to the fact that you get a dominated splitting. So there's kind of like an oscillator style theorem going on behind here, if you like. I've got to be careful here. If I use too many dynamics words, you're going to ask me what they mean. I'm going to embarrass myself. I only recently learned that singular values and eigenvalues are really different. So what this tells you is that every element is loxodromic, meaning it's diagonalizable over R with distinct eigenvalues. And it tells you this is a discrete faithful representation because those eigenvalues are growing coarsely like word length. And moreover, it tells you that the embedding of the map of gamma, the orbit map of the fundamental group of surface into the symmetric space is a quasi-isometric embedding. And remember, that's a really nice property of convex co-compact Fuchsian groups, that they're quasi-isometric embeddings.
So that's a map of the downstairs thing, or that's upstairs?
Well, you can think about it. If you take a map of the representations of map into PSLDR, and if you think of that, a left invariant metric on there, the representation itself is a quasi-metric embedding. Or you can think of the orbit map, which takes the group.
Which orbit map? Orbit of what on what?
So if you take pi1 of S acting on the symmetric space of PSLDR, then that maps.
By the compacts up there.
Right. Then you could take an orbit embedding into that symmetric space.
Well, what's the orbit embedded in?
Well, you just pick a point and you look at its
Which
orbit.
one, where? Which one are we talking about?
You just take any point in the symmetric space.
No, it's an embedding of something in something else, isn't it?
Yeah, I mean, so you could think about
embedding
if you have
what and what?
If you have a group acting on a space, you could always look at the orbit map, which is you just pick a point in the space, and then you can map the group into the space just by mapping the element gamma to gamma the base
orbit.
The gamma.
Right.
Yeah, orbit. And that gives you a map of the group into the space, and that map is a quasi-isometric embedding here.
No, but what's the domain and what's the range of this map?
Domain is pi1 of S.
What?
Domain is the fundamental group of S with the word metric.
Ah. Oh.
Yeah.
And just the orbit.
And the range is the
Letting
symmetric space.
the group act is
Yeah.
isomorphism on the group. I mean, quasi-isomorphism.
Yeah.
Okay.
And moreover, you get a limit map. This is something we're also used to from Fuchsian groups or Kleinian groups. So if you let FD be the flag variety, remember a flag is just a line inside a plane, inside a 3 plane, inside a 4 plane, up to a D plane. Okay? And so now we can get a flag by, if you look at a tangent vector in T1 of H2, which is the G's joining Y to X, then you look at the splitting over, you look at that splitting LK tilde V over that tangent vector, and that gives you K vectors. D vectors. And from D vectors, you can make a flag. Well, the line is spanned by the first vector, the two plane is spanned the first 2 vectors, etc. Now, it's not obvious that that's well defined because I'm using the point Y, but the contraction properties tell you that this is a well-defined mapping. So you get this nice equivariant map of the boundary of H2 into the flag variety. And this is almost equivalent to the splitting fact we had there. It's very closely related. In fact, if you're an irreducible representation, they're the same thing. So by the existence of that splitting goes by the name of being an Anosov representation of the spectrum minimal parabolic, if you've heard those words. So this map is well defined, and the contraction.
What property earns it that name?
The splitting. The splitting, one way of saying, whenever you have something which is an Anosov with spectrum minimal parabolic, you have a splitting of the flat bundle. So this is part of the theory of Anosov representations. But I guess I made the choice not to mention that, which was probably a good choice. like in the slides, but
Anosov has this picture, I don't see that picture yet in this story.
oh, we'll see it in a minute.
Okay.
You'll see it in a minute. So this is held a continuous, and this also has this nice property of being transverse, which is if you take the k plane at one point and the d minus k plane at the other point, they span. So any two distinct flags in the image are transverse. So this is very strong property. And this map is also, from the Fock contract viewpoint, it's a positive map.
It's what?
It's a positive map, which is positivity is some kind of generalization of combination of transversality and monotonicity in appropriate coordinates. Okay, so now Andres took this picture and showed how you can take this picture and you can make a geodesic flow, in fact a whole bunch of geodesic flows, which are associated to the which are held or orbit equivalent to the unit tangent bundle of S, which just means you take the unit tangent bundle of S and you travel along it at different speeds. That's what held or orbit equivalence means. And the periods of this flow are going to record spectral data, and these flows are Anosov flows. So you're seeing an Anosov flow sitting here. And let me give you just the simplest.
These are reparameterization of the geodesic flow?
Yeah, it's just a reparameterization of the geodesic flow. And we're going to see that this one I'm going to describe is just going to pick off the top eigenvalue. Its periods are exactly going to be the logarithms of the top eigenvalue.
And the decomposition that you had before, with all these eigenvalues, so it's clear which one are going to be larger than 1, smaller than 1?
Yeah, no, that's not clear.
Ah.
That's not clear, yeah.
What was just said?
He was asking, what if the eigenvalues, can you tell if an eigenvalue is less than 1? So first, if you take the Fuchsian representation into an odd dimension, it will have an eigenvalue of 1. And that eigenvalue could kind of go either way, right? When you deform it, so you really can't
It's
tell.
depend on the D.
Well, no, I don't think it does. I don't think you can tell. The ordering doesn't change, but I don't think you can tell.
No, but what are you guys talking about now? Which representations are you considering?
He's asking me, can I always, so first I have a representation into PSL3R. Can I always say can I say that the middle eigenvalue is always bigger than 1 or less than 1? And I'm saying, no, I don't think I can. And I think it could be either.
You have an also, you have this expanding direction and contraction, which is the dimension of each one.
Yeah. So you know that like, from just by abstract nonsense, you know that the L1 line bundle is itself contracting.
Yeah.
But the other bundles you don't really know. So here's something that this is obtained from the L1 bundle. And so what Andres does
What's
is,
an L1 bundle?
sorry, the L1 bundle is the first line bundle.
Oh,
The first bundle in his splitting. So what he's going to do is he's going to define a principal R bundle over the set of distinct points in each 2, and he's going to let the fiber be, if you take xy, you should take a vector tangent to the g subjoining y to x, and you take the fiber to be L1 tilde minus 0 by plus or minus 1. That's what the fiber is. So I told you at every point what the fiber was. There's a group action on that fiber, so you get a quotient, and there's a flow. So if you're essentially saying above each point I have R plus, right? What's the only really sensible flow on R plus? It takes W to e to the TW, and it does nothing on the first 2 factors. So again, it's kind of the stupid flow upstairs. But if you look at it, if you look at some point gamma plus gamma minus W, then eta of gamma goes to gamma gamma plus, gamma gamma minus, rho gamma W. Well, that's gamma plus, gamma minus, and since W was an eigenline with eigenvalue lambda 1, we get lambda 1 W. Oh, that's exactly phi log lambda 1 eta.
I'm totally lost. Not a question.
Okay. So let's go back here
Can
to.
you just, rather than proving it, make a statement about something?
So what I want to say is I defined
No, we just make, there exists something, some property.
So there exists a geodesic flow,
Yeah.
which is Helder orbit equivalent to the
I
universal
mean, that's
tangent
already a
bundle.
bad way to say it, because the maps, it doesn't change any of the orbits.
Right.
So it's not equivalent, it's, the equivalence is almost the identity on orbits, right? It is. the
No, no.
identity.
Well, isn't the identity on the orbits? There's a time change.
No,
It's a
on the orbit,
reparameterization.
it doesn't change the orbit.
It changes the period, though.
Yeah, yeah, but it doesn't
But the
change
periods are
orbit.
what we care about. So the key
No,
thing
but
is,
it doesn't change the orbit, so it's not an orbit equivalence, it's the identity on orbits. It's a reparameterization. So, I mean, it's not an interesting orbit equivalence, so it's already,
Orbits are already identified.
I mean, it's just.
right, but isn't that what dynamicists call this? I didn't invent this.
No, it's a
So
very
flow is
special case of
important.
orbit equivalence.
When you have a flow, you have to take care about the time that you are going to, the period that you're going to have your orbit. The orbit is the same,
Yeah,
but what's important is the periodicity.
I thought that's
So
what
this-
orbit equivalence meant.
Not in the flow, in the D view, in the map,
Oh, okay.
makes sense.
Let me use the word,
Yeah.
so it's a reparameterization. It's a reparameterization of the unit tangent bundle, and now the periods
Of the geodesic flow.
of the geodesic flow, and the periods are the logarithm of the first eigenvalue.
Yeah, okay, sure, but then, okay, but-
So now I've got this geodesic flow,
Mm.
and it's
so it's a
recorded.
reparameterization such that,
The periods are the logarithms of the first eigenvalues of each element.
what was that? I mean, periods, it's a whole set of numbers, so
Yeah.
it's equal to some fixed number.
Well, so if you take a period associated with the group element gamma, its period is log of the first eigenvalue of rho gamma.
Oh, okay.
So
You
I've
mean
got
the biggest one or the smallest one?
the biggest one,
Okay.
yeah. Okay. So, in fact, there's a generalization. So, in general, if you look at never go a little too far. There's a Cartan subspace, which sits inside the Lie algebra. You think of it as the set of trace-free diagonal matrices. And there's a Jordan projection into this, which takes an element, just the logarithm of its generalized eigenvalues, log lambda 1, log lambda 2, log lambda d of A. And what Andres does in general says that if I take any good linear functional, so a functional that's positive on the non-negative on the Weil chamber, then I can define this flow space, which is a reparameterization of the unit tangent bundle, and the periods are exactly given by phi of the Jordan projection of rho gamma. So for any linear functional on the eigenvalues, I can obtain a flow space, which is pretty cool. And so part of this structure is, oh, no, that's not, okay, part of the structure is here, we're going to start with a collection of representations, and we're going to turn it into a collection of dynamical geodesic flows. And then we're going to get access to all of the thermodynamic formalism, and we're going to do all sorts of stuff with it. That's sort of the philosophy.
Okay. Because the entropy changes when you reparameterize and stuff like that.
Right, yeah, so we'll be talking about entropy, just, I think on the next slide, I don't remember for sure. So in particular, yeah, there we go. In particular, you get all these counting results. So you can think of these things as there's a lot of, you can think of this linear functional as giving you a notion of length. So one notion of length would be look at the log of the top eigenvalue. And that's roughly the same. In PSL2R, that's just path to length, right? Or you could look at log lambda 1 over lambda 2. And in PSL2R, that's exactly the length. Or you could look at log lambda 1 over lambda d. And all these are reasonable notions of length. In fact, there's kind of a whole d-dimensional space of notions of length here associated to any linear functional. And now you can talk about the entropy of this flow with respect to any of these notions of length, and you can count with respect to any of these notions of length. So if you look at instead of all conjugacy classes, such that phi of nu rho gamma, so if you like that, whenever you see that expression, you just think log lambda 1 rho gamma, because that's the simplest example of a linear function. That's less than or equal to t, and then the so-called phi topological entropy is just the exponential growth rate of the number of things of length less than t. And then, Andres, now that we've got an Anosov flow, bang, you hit it with the thermodynamic formalism, and you get this counting result, which generalizes counting results from Teichmuller surfaces. The number of closed orbits of length less than t grows exactly like e to the entropy times t divided by the entropy times t. Notice that for a closed surface, the entropy is always exactly 1, and you get the classic formula, which I think goes back to Dani, was generalized by Margulis, that the number of closed g's of length less than t grows like e to the t over t.
So this part is basically built on the fact that he managed to show that this flow is Anosov.
Yes, right.
And then appeal to the...
Right, so the thing is what you want to do is once you have an Anosov flow, which is recording spectral data, now you can count according to that spectral data once you show that flow as Anosov. That's exactly what he does. So now, once you've built this flow space, which seems like kind of like, okay, why do I care? But the reason you care is because this flow space is Anosov, and now you've got everything Bowen, Ruel, and Perry, and Polycott, and all those guys did, and you get your hammer out and you start hitting things. Yeah. Does that make sense?
So the entropy also have this characterization in terms of the eigenvalues.
Yeah, it's related to the eigenvalue. Yeah.
And this will depend also the dimension of the unstable erections. Because it's related to the sum of the logarithm of the eigenvalues. And so if you have many unstable erections, well, your entropy will be large, and so the counter will be different.
Yeah, you can get different entropys for sure. Yeah. Okay, and now, so what's really sitting behind this slide is, I'm going to maybe tell part of the story ahead of time, but Thurston, when he was doing, one of the things he did when he was starting Teichmuller space, among many things, is he constructed what he thought was a new metric on Teichmuller space. And he said, well, just take the length of a random geodesic and take its Hessian.
Say again, take what?
Take the length, this is going to make this one way to explicit, because the first thing you're like, what do you mean by that? You take the length of a random geodesic, you take so if you have a fixed metric, then you can take the length of the you take a random geodesic in this metric.
Closed? Or
Well,
what do you
he
mean by
doesn't say.
random geodesic? What do you mean? No, what do you mean by the word
I'm
geodesic?
going to make it precise in a minute.
I don't want it precise. What do you mean by the word geodesic? Between 2 points or closed one?
You know, one way of saying what I mean is say the Liouville current.
What?
One thing you could say is the Liouville current on the geodesic, on the unitangent bundle. That's kind of one way of saying it. But one thing you can say.
No, I'm not asking for what random means. I'm asking what you mean when you say that a random. I know what random means and what it will mean. When you say a random geodesic, what do you mean by that word geodesic in that moment?
Oh, okay. One way of thinking is suppose you take a sequence of geodesics, which are becoming
I don't know what you mean by
equidistributed.
geodesic.
Oh, sequence of closed geodesics becoming equidistributed.
Okay, fine. That's what
But I think you don't, but like the Liouville current, you don't have to think of it in terms of closed geodesics, so anyway. But, so if you take on a sequence of equidistributed geodesics, and you look at what happens, you look at their length in your metric, and then you look at your length from the other, the ratio of the length from the other metric, that gives you a function on Teichmuller space. It has a minimum at your base point, and you take the Hessian of that function. And he said, oh, that's going to give me a Riemannian metric, which is mapping class group invariant. And Sullivan said, and not Sullivan, Wolpert said, well, that's just the Weil-Petersson metric. And it turned out he was right, that the Weil-Petersson metric, which is defined in terms of quadratic differentials, and
Which is incomplete.
the hyperbolic metric, yes, which is incomplete. Right, so.
You take the Hessian and then you take an eigenvalue of the Hessian?
No, you just take the Hessian, that gives you a form on, that gives you quadratic form on the tangent space. Yeah, I'm going to be more explicit about it here in just a minute. I was just trying to say, what Thurston always said was, you just take the Hessian of a random geodesic, that's all he said. So, I was trying, so I'm trying to be Thurston, I'm not Thurston.
And I wouldn't let you.
Dennis said, I know Thurston and you're not Thurston, basically. Anyway, so another way of making this precise is to define what we call the pressure intersection. It's a bad name, I regret it, but it's the name now. Is when you look at all curves of length, it's a function on a pair of Hitchin representations, and then you take all curves, instead of taking the equidistributed sequence, you take all curves of length t, look at the average ratio of lengths in one metric. So the curves are of length t in rho, and look at the ratio of the
They are curves of time t. Time t?
Of length at most t.
Length at most t.
At length at most t, and then you look at the ratio of the length. And typically, if you take the curves of length t over here, most of them will get longer in the new metric, and there'll be new curves of length less than t over here. So you expect this ratio to be typically bigger than 1. So, so this is one reason you call the intersection is because for hyperbolic surface, this is just the intersection in the sense of Bonohon and the geodesic currents.
In the sense of what?
Bonohon just got.
Yeah.
And so if you take the Liouville current of two Fuchsian representations, this is that intersection. But this is not symmetric, for instance, whereas that one is. So it's a bad name. And it turns out now, this works just fine in Teichmuller space because everything is entropy 1. But to make this work nicely, you've got to normalize it by the entropy. Okay? And so that's a function on the Hitchin component cross the Hitchin component. And so you could show, this is what I was saying, this renormalized entropy will always be at least 1, and it will be exactly 1 on the diagonal. So now if you fix your first factor and look at the derivative of that at rho, that will give you a non-negative quadratic form because it's a minimum, because you're at a minimum of the function. Now the problem is, so more prosaically, this is the way I like to think of it. A tangent vector at rho, at tangent space to rho non in Teichmuller space, is a tangent vector to a path of representations, right? And now you just look at J, to get a P phi of VV, you just take the Hessian, you take the renormalized entropy of rho naught rho t, take its second derivative at 0. Its first derivative is going to be 0, its second derivative is going to be greater than or equal to 0, and you square it. So that's very concretely what it means. You just look at a path of representations.
So this idea also goes back to the thesis of the least quality.
Oh, does it?
Yeah. I mean, for a Teichmuller space itself.
Oh, interesting. Because where we learned this, I should have this on the slide, where we learned this was in McMullen's work. So I should have this on the slide. But McMullen did the same procedure to reinterpret Thurston's approach to Teichmuller space from a thermodynamical viewpoint. And so I have to look at the paper. And then Martin Bridgman did it on quasi-Fuchsian space, and then we did it in the generality for the Hitchin component, and more generally for spaces of Anosov representations. And like I said, the hard work in these theorems I'm about to put up So the hard work in the theorem I'm about to put up is to show that what you get is actually a Riemannian metric, because you could have this Hessian having degenerate directions, and in general, it will sometimes have degenerate directions. So you notice that, for instance, if you take lambda 1 minus lambda d, well, if you sit on the Fuchsian locus and you take a set of representations started there, and then you take its sequence of dual representations, this will be symmetric about that, and that will give you a zero vector from this viewpoint. But now, we only have really studied 3 functionals. The first one is log lambda 1. The second one is log lambda 1 over lambda 2, and the third one is log lambda 1 over lambda d. So in the case of log lambda 1 and log lambda 1 over 2, this gives you a non-degenerate Riemannian metric on the Hitchin component. And of course, that in itself is not that interesting because it's just Euclidean space. But this metric has the property that it's mapping class group invariant, and it restricts to a multiple of the Weil-Petersson metric on the Fuchsian locus. So you've taken the Weil-Petersson metric on the Fuchsian locus and extended it to a metric on the full Hitchin component.
Constant multiple or functional?
Constant multiple. Constant multiple, yeah.
So sorry, kind of little lost. So in the previous slide, so you have this function that is, you have 2 representations, you associate this function between those 2 representations. And you start with the Fuchsian situation, not invading, not deforming it. And then this number will be increasing when you start to deform. How is it?
Well, I say if I stand, or if I fix this factor, and I start on at the diagonal, it's obviously 1.
Yeah.
And then if I go in any direction, if I move the second representation in any direction at all in the Hitchin component, it can only get bigger. We can't say for sure it doesn't stay 1. So now what you do is you've got this, you can think of, you fix this point, and you've got this function of just 1 component, and now if you take the Hessian of that along the diagonal, that's going to give you a quadratic form on the tangent space to your base point. And that's going to be a non-negative quadratic form. Does that make more sense?
Yes.
Okay.
Good.
Yeah. And then the hard part is, why isn't it degenerate? And sometimes it is. So for instance, if you take the so-called Hilbert linear function, which is log lambda 1 over lambda d, then it will be degenerate, but you can in fact show that its degeneracy is very controlled. So it gives you a path metric. So if you take a point, 2 different points, and you kind of integrate this along any path joining them, the infimum is going to be greater than 0. So it actually, so if you have just a form which is just non-negative, you get like a pseudo-metric, right? The distances may be 0. So we can show this is actually honestly a metric, and then it's a Riemannian metric most places, but there's some 0 vectors in there, so it's really not quite a Riemannian metric in that case. And some of this was done in more recent work with my junior. I feel a little bad. I reconfigured this talk in a way which I spend much less time talking about my junior co-authors, but I was, I wanted to. Pretty soon I'm going to get to what this has to do with Dennis's previous work. And I wanted to get there, and I also wanted to make it, well, hopefully more understandable. So remember Harry Bray, Nyima, and Giuseppe Martone, and I said their names loudly. Okay.
So when there are 0 directions, the rank still changes, right? It's not as if the rank remains, rank of the Hessian, does it remain constant?
No, yeah, it won't change, yeah. Because what's actually happened in these cases is almost everywhere it's non-degenerate. There's some kind of isolated places and isolated directions where it is degenerate, but not so much you can never make a path of 0 length. Yeah. Okay, and then Raphael Potri and Andre Sambrino came along, and they showed that if you have a Hitchin representation, you look at, well, alpha k is log lambda, log lambda k over lambda k plus 1. The one we care about is alpha 1, log lambda 1 over lambda 2. Then the entropy is 1 for every Hitchin representation. So now, well, maybe this is a little bit more like Teichmuller space. So maybe this is actually the right link function here. And there's a nice conjecture here, which is that there's an upper bound on the length, on the alpha 1 over alpha 1 length systole, all over the entire Hitchin component. And we checked that for a few one-dimensional Hitchin components, and Anyway, this is a conjecture I'd love to solve. I don't know how to do. And what they show.
Paraphrase it,
What?
paraphrase it.
So is there some number 87, so that if you're a Hitchin component into PSL3R of a surface of genus 2, then there's always some element so that log lambda 1 divided by log lambda 2 is less than 87. Well, there's some notion of length. There's always a curve of length less than 87 for this notion of length, where the notion of length is alpha 1 over log lambda 1 over log lambda.
So this is like a system.
Closed curve.
Right, the system. So it's not true if you take log lambda 1, that's false. This conjecture is false. If you take log lambda 1 over log lambda d, it's false. But it appears to be true for log lambda 1 over lambda 2. Anyway.
No, but paraphrase it. You're sort of saying there are no short curves in some sense or something?
No, I'm saying there's always so this is like the Bayer's constant, right? There's always a curve of length. If you take any surface of genus 3, any hyperbolic metric, there's always a curve, at least one curve of length less than 10.
Yes.
And so this is kind of like, you would think that if you blow up all the curves, the entropy wouldn't stay 1, right?
So you mean that so the representation will not go crazy
Right.
instead of the length?
Yeah, but I don't understand the statement, see, so. What's the qualitative statement?
That there's some nice notion of length, so that every Hitchin representation of a surface of genus 3 has a curve of length less than 87.
Less than some
Some universal constant, yeah. Depends on the genus and the dimension. Just like in Tengren space.
Every Hitchin component, there's some of these, one of these notions of length we talked about, which will see a universally long curve.
Yeah. Yeah.
I mean,
Yeah. And so they showed more generally that if you take most of these other notions like log lambda 1 or log lambda 1 over d, then the entropy is 1 exactly when you're Fuchsian, and otherwise it's less. This is a beautiful rigidity here in the Raphael. So now,
but is there exist in that statement?
it says the entropy, so if you take phi log lambda 1 or log lambda 1 over lambda d, then the associated entropy, which is the exponential growth rate of a number of phi curves, that length is always at most 1, and it's only exactly 1 when you're Fuchsian. Oh, actually, I've misstated. That or phi lies, there needs some normalization on that, sorry. So it's not quite true the way I stated, but I didn't put enough normalization.
Those caption is incredible.
I'm pretty sure I didn't say that. I do not remember saying that. Okay, so we're getting almost out of time. But let's.
What, do you remember saying that?
Yeah, I do remember saying that. Well, so let me now say how this would link up with some work.
You thought that.
Yeah, I didn't think that. That was about you.
Maybe this is the way they understood Fuchsian.
So I want to talk about how one might use, now the problem with these pressure metrics is we don't really know anything about them. That's the problem. Let me tell you an idea, and approach this through some previous works of Dennis's, which no one's gotten that far with yet, but I think is quite promising. So you can think of a unit tangent bundle as being foliated by copies of H2, just the central stable manifolds. You just take a point in the boundary, and all the tangent vectors to GD extending at that point is your central stable manifold. And so you can think of this as a foliation, you can think of the unit tangent bundle surface as a foliated space where each space admits a complex structure. Okay? And then Sullivan developed a theory of the Teichmuller space of such objects, which includes notions of Beltrami differential, quadratic differential, and hence the notion of Weil-Petersson metric. So,
Oh, I'm trying to recognize what you're referring to. You mean
To Riemann surface
something
lamination.
foliated by complex manifolds?
yeah,
Okay.
yeah. So a lot more work has been done on this in the case of the solenoid by Dragomir and some other people. But what we're going to care about is thinking of the unit tangent bundle as a complex foliated space and its Teichmuller space. So now, since the entropy is 1, it turns out one can then use that to identify the central stable manifolds of this San-Marino geodesic flow with H2. So now you have, again, a space foliated by H2. And Candel says, well, if you can do that, you can think of it as a complex foliated space in a way which fits in with Dennis's picture. So now, before we had embedding Hitchin component into the space of dynamical systems, or you could think of it as an embedding in the space of Lipschitz cohomology classes of potentials or something, but now we're embedding it into Teichmuller space. And what Nicola Tolazan has proven, but unfortunately not written down yet, is that the pressure form that we define in this dynamical viewpoint, if you look at its pullback under this embedding, is sorry, all the way around. The pressure form we define is the pullback of the Weil-Petersson metric and Teichmuller space up to scale. So that means that you could attempt to study this pressure metric using the kind of classical techniques that a lot of people in this room have developed, right? So, and then, and what I said I would talk about was augmented Hitchin component. So let me, just so I mention my other co-authors. So, here's another, so along with Andy Zimmer and Tengren, we generalized this Potry-San Marino theorem into the setting of Hitchin representations of Fuchsian groups in general. And that's what I said I would talk about. So, but I better stop.
There's this big algebraic group that's associated with Hitchin representations and things like that, moduli spaces. And it's kind of sophisticated representation theory, algebraic geometry. And then now there's this army of Thurston dynamical hyperbolic people coming in and analyzing these things. Do these two groups really communicate? So sort of a community question. I mean, it's
Yeah.
interesting to me that these two very diverse
Well, I
set
think,
of ideas are now merging together.
well, I think, you know, there are some sense different schools, but there's this real natural intersection point, which is Andreas San Marino and Francois Weil-Petersson, both of whom had very strong geometric understanding and also a strong,
Algebraic. Yeah.
also strong dynamical background. And so I think what's
Laverie had strong algebraic
yeah,
background.
that too, yeah.
Right.
So I think what's a little bit different maybe, for instance, which I don't understand at all, is this more analytic Higgs bundle approach. And that is really a technology beyond beyond the scope of my expertise. So I think that group kind of sits a little separate
That's
sociologically.
related to theoretical physics.
Right, so the stuff that comes out of Hitchin. But Laverie understands that stuff too, because he's Francois Laverie.
It's funny what you say, Andrés San Marino, he studied first in Uruguay with the full dynamical system community, kind of very related to what Magnier had done.
Yeah.
And then he went to France for his PhD, and he started with Laverie, etc. And this is
Well, Laverie,
how
he
he
was-
made the connection.
Yeah, he was trained by Jean-Francois Camp, who, so he has this very heavy symmetric space,
Homogeneous space.
homogeneous
But
space.
basically, it was
background.
all the school that Magnier developed.
Right.
They went
So
from
he had
Brazil,
that
Uruguay, and
background.
then he went to France.
Oh.
And this was where the communication happened.
So is that how the connection was made? Was the Laverie the first one to make the connection, or was San Marino? between
Sam-
an algebraic group.
Well, I
and-
mean, Sam Marino's stuff with the music flows is in his thesis. So that predates Labrie.
Oh,
So,
okay.
and what actually happened is
He
Martin,
came from Uruguay with Lepowski, what's his name? With, you know, the famous, the guy who proved.
McGinn, no, who? Lebovich.
He died now.
Yeah, Lebovich.
Huh?
Lebovich.
Yeah, so he's in that school,
Yeah.
very dynamical, proved, you know, expanding map is pseudo-Nassau, the surface.
and so Andre started out with Jean-François Ken, did all this
In
stuff.
France, he got an algebra side.
Yeah, and then he went and worked with Francois Labrie, and then Martin and I were starting to talk to
Okay,
Francois about kind of generalizing Kurt's work. And,
Right.
and then once we were trying to generalize Kurt's work, well, Andre was his postdoc, so it was kind of very serendipitous. I don't know how far we would have gotten if we hadn't talked to Andres about it. So it just was all very lucky.
No, it's sort of remarkable that something invented by the algebraic physics point of view has all this Anosov structure.
Right, yeah, so I mean, from Hitchin's viewpoint, there's no reason to expect all these dynamics is going to be there, right?
Right.
You can't see that from the way he introduced them.
The structural stability, right, it keeps moving out
Yeah,
as long as you deform.
yeah.
So earlier in the talk you said that the Hitchin component is real analytically homeomorphic to Euclidean space of certain
Yeah.
dimension. Does it have any kind of natural complex structure?
Well, it's a symplectic structure.
Symplectic, but not.
What was the question? I didn't hear it all. Well,
He's asking if it has a complex structure. So
what's
the
it?
Hitchin component has a complex structure. And it has a symplectic structure coming from the Goldman viewpoint. And you really want to, I mean, in some sense, it's naturally a real object, and it sits within a complex object, which is the PSLDC character, right? So it's in some natural sense the real points of a complex object. So like I have a graduate student now, and I'm encouraging them to work on kind of understanding what are called quasi-Hitchin representations where you deform into PSLDC. And of course, then you are going to not get the entire component. You're going to lose, you know, you're going to deform to discontinuity, to indiscreteness in those directions. But yeah.
The dimension can be odd sometimes, right, according to your formula.
No, d squared minus 1 times 2g minus 2.
Yeah, it's even.
That's always even, yes.
There's a 2g minus 2
For
factor.
every d?
Yes.
Yeah.
Well, 2g minus 2 is always even. And odd times even is
Oh,
even.
yeah,
Sorry. I had to take my shot.
It's an ideal.
Yeah.
So usually these representation spaces are quotients of algebraic variety, so they have singularities in general.
Right.
But what makes the Hitchin component smooth? Why is it that that's
Oh,
not
it's a Poincare duality fact, yeah. So it's true. It's true that if you look at it here, if you have a representation variant of a surface group into anything sensible, all the irreducible points will be smooth points because you can do this. You just do these cohomology.
So it's similar to what happens to Teichmuller space versus moduli space. Right? The moduli space can have all these singularities.
Right.
Teichmuller space is.
You're not modding out by discrete groups. You're modding out by. So you're using like the slice theorem, basically. So yeah, so you can defend. I mean, just for representation varieties, there's cohomological ways of detecting singularities, and the cohomology of a surface group is simple enough that you don't have them. This also works if you take a three-manifold with non-empty boundary, you get similar facts. But in general, if you work with more complicated groups, you're going to get singularities. Yeah, and all of this stuff's going to be a mess. So we can't handle, in the more general case, we can't handle points in the representation variety where the singularities occur. We don't know how to extend the metric across that or anything.
For example, are the other components smooth manifolds?
I don't think so, no. Because I think first of all, when you're doing this conjugation, all hell breaks loose at the elementary representations. And so then you got to decide what to do there. that's why the whole GIT quotient thing comes in. But of course, we can't really do GIT quotient because this is a complex variety.
Oh,
Yeah, yeah. I don't really know.
Is that, it's a problem even for PSL2R?
Yeah, yeah. I think even for PSL2R, you probably have bad points, but I'm not sure. I think certainly the elementary representations are not smooth points. Almost no matter what you do with them. I'm just sort of dredging up vague memories of things people have told me at this point.
May I ask one more quick question? So you have this representation of phi 1 into PSL2R, and then you compose it with this irreducible representation of PSL2R into PSL2R. Is that composition representation, is that completely reducible to lines?
What?
Does it break into direct sum of lines?
Yeah, that's what he said. That was what you said at the beginning by this quadratic, what do you call it? This
They're using the Veronese embedding, I mean.
Veronese embedding, because you have Li tensor Lj. So you've got quadratic thingy.
Yeah.
And he said, I'm just trying to extract what he, you
Well,
remember the proof.
Let me say something really concrete.
Yeah,
There's a really
right.
concrete way to say this. You get a map of the boundary of H2 into the flag variety, and this is exactly given by, you take a point, any point in the boundary is an attracting fixed points of a hyperbolic element. You look at its image under the irreducible representation, that's a loxodromic element. So it has an attracting flag. So you just take the attracting point to the attracting flag. That's the map. And so it's just something very concrete. And you call that that's called the Veronese embedding.
But now we'll split the first line, and then you need to form this, and then this splitting persists.
Right, and so now if you have a pair of
Stability
points,
somehow.
so now if you take a pair of points, so you take a hyperbolic element and you take a pair of points, and they go to a pair of flags here, and a pair of flags gives you a splitting, right? And that's how you get it.
Transversal.
Yeah, you just take, you just do all the intersections. Yeah.
Okay.
Any other question?
Oh, wait.
Okay, go ahead.
No, I had some questions.
Yeah, go ahead.
But, so, Edson asked if this is complex. He said, well, it's even dimensional, but you don't know if it's complex, but it is symplectic, right?
Yeah.
And then there's also a Riemann surface lurking in this discussion. So it's kind of a compact surface. So we have a symplectic manifold, and we have a Riemann surface.
So maybe there's a Caylor structure.
So then there's this field called symplectic topology, where you consider all mappings of a surface into a target space, and you look at the ones that are J-holomorphic, and you get moduli spaces. Is there any...
You're above my pay grade.
Has anybody thought of that?
Not that I know of. People have,
What?
people have looked at the symplectic structure some, but I know if they've done it from the point of view of pseudo-holomorphic curves and that sort of thing, that I don't know.
Can you use these pseudo-holomorphic curves to define some kind of a metric on the space? Or?
What?
Can you use these pseudo-holomorphic curves to define a metric on the target for them?
Is the question, can you use pseudo-holomorphic?
Yeah, to...
I don't know.
I mean,
One thing I'll say is from Hitchin's work, there is a complex structure sitting there. What he does is he proves that the Hitchin component is identified with a space of differentials over a surface. But this whole picture involves a base surface. So he ends up with sort of kind of a complex structure, but one which is not mapping class group in any real sensible way. So he ends up with, there's an actual metric associated.
As far as you know.
I think it's
It's
not.
hard to prove a statement like that.
Yeah. Well, but he ends up with a metric, which I think we know is not mapping class group invariant, the Hitchin metric. So there's kind of this whole viewpoint, but the Hitchin viewpoint doesn't interact well with the mapping class group. So for someone like me, it's like,
Yeah.
But to a physicist, actually, they don't mind. Like, you know, Andy Knightsky studies the Hitchin metric and stuff, and I think it does have content if you care about this from a viewpoint different than the one I come with.
Yeah.
So I don't want to appear to be poo-pooing that work. It's just not, it's not the way I think about things.
Any other questions?